Hello everybody. Welcome to Rocket Science 101 Part 3. We'll be talking about basic physics today that describe a rocket's flight. Um, and you will notice, first of all, that I'm using a PowerPoint this time. I think this will be more streamlined than those 8.5 by 11 pieces of paper and a Sharpie marker. I think this will be more organized. So, let's jump right into it, starting with Newton's three laws of motion. You probably have heard of Isaac Newton before, but he's one of the most famous physicists of all time because he basically came up with all the basic laws of physics and mathematically described gravity, something that nobody else had been able to do before. So I'll just run through these laws real quick. His first law states that the velocity of a body remains constant until it is acted upon by an external force. So now that might be common sense to you and me, but back in his day, the common belief was that an object's natural state was to be at rest, because, of course, you toss a stone and it will skitter to a stop eventually. But that's because it's being acted upon by gravity, kinetic friction, and so those are those external forces that will change its velocity. So that's pretty basic. His second law puts this external force F into more mathematical terms. F is equal to the mass of the object times its acceleration. And this will be the net force, because you can have multiple forces acting on an object. And remember, force is a vector, so you do vector addition to find that net force, and then the resulting acceleration, which is also a vector, comes from that net force. Okay, so his third law talks about action and reaction forces. You know what I'm talking about if you've ever fired a gun. That recoil is the reaction from the force of accelerating the projectile. And this is exactly how rockets work. Without Newton's third law, we would never be able to reach outer space because rockets would not work. The force of accelerating the exhaust out the nozzle will result in the reaction of flying forward. Now I'd like to talk about his second law, and it's actually more fundamentally stated as a change in momentum. So here I have, these aren't negative signs, by the way, those are just like a bulleted thing here. But anyway, starting with force equals mass times acceleration, remember that acceleration is a change in velocity, and here this quantity momentum is mass times velocity. So it has to do with an object's own inertia and how fast it's moving. So a change in momentum would result in that object's change in velocity. So if we take F equals m times dv dt, that m dv is dp, so it turns into dp dt. So this will become useful in a moment. So why is this useful? Well, because we can then find a change in velocity from a force sustained for time t. This is the impulse momentum theorem. So if we have the thrust of our rocket sustained for time t, we can find its resulting change in velocity. But before we get to that, let's talk about the forces acting on a rocket, because it's not just the thrust that's involved here. For instance, we have the weight of the rocket, we have the aerodynamic drag, the air resistance blowing on the rocket, and we actually have lift, but I will be talking about this in more detail in a later lecture. and it really doesn't affect the forward motion really. It's perpendicular to the flight path. It turns out that this lift is just for stabilizing the rocket, and as I said, I'll cover that in more detail later. So basically, we only need to worry about three forces when we're looking at the acceleration of the rocket. So, our equation for a change in velocity is this change in velocity equals the net force dt divided by m. So, maybe you don't know where this is coming from. So remember, force equals m dv dt, and we want to solve for dv. So dv equals f dt over m. That's where that comes from. Alright, so from this velocity differential, we can describe the rocket's trajectory, and I should probably mention, as I say here, that we have lots of assumptions in there, such as no wind, because we ignored lift. What else? Something else. I know it's oversimplified, but it describes the theoretical flight of a rocket quite well. Alright, Newton also talks about gravity, and he came up with this formula for gravity, the force of gravity between two bodies. This g is a constant. It's the same on every planet, on every moon, every star. 6.67 times 10 to the minus 11th with these units. And if we have different units, this number will change. But we typically, in physics anyway, work with the metric system. But in engineering, they tend to work in the English system. But I think that's stupid. I think we should work with the metric system. I like it better. Anyway, the mass of one body, the mass of the other body, and it's inversely proportional to the distance between them squared. So here's one body, here's the other body. When you increase the mass of either body, the force increases, and when you shrink the distance, it increases. I guess that's all I want to talk about this. Oh yeah, and then there's when you're just on the surface of the planet, this whole thing is pretty constant, right? The mass of the Earth doesn't change, and the radius of the Earth isn't changing much either. So this turns out to be the gravitational acceleration g, which on Earth is equal to 9.8077 meters per second squared. And then calculating the weight of something becomes rather easy. The weight is just equal to the object's mass times this gravitational acceleration. Hey, remember? Force equals ma. Ta-da! Let's see, what else was I going to talk about? Oh yes, energy. Energy is the ability to do work. Well, what's work? Work is a force times a displacement. So if we have some object here and we're pushing on it with force F, the work that we do on it is that force times how far we push it. Alright, so let's talk about this energy in more detail. There are several types of energy, but I'm gonna mainly talk about potential energy and kinetic energy. So potential energy is energy based on an object's position relative to either a gravitational field, or maybe it's a spring. Like if you've compressed the spring, it has potential energy, or maybe it's in an electric field, or etc. Um, I'm basically just going to talk about gravitational potential energy right now, and that is equal to an object's mass times acceleration times how high it is above the deck. And then there's for a spring, but I'm going to ignore that for now because that doesn't really have to do with rocketry. Kinetic energy. That comes from an object's motion. So it actually increases with the square of velocity. So if you double your speed, you increase your kinetic energy by 4 times. But if you just double the mass, you only double the kinetic energy. So there's this theorem that work energy theorem, work kinetic energy. The work done by a force can be related to its changing kinetic energy. Ta-da! Now, pretty much every quantity in nature has a conservation principle, which just means that it can't be created or destroyed, so it has to be conserved. So the total energy at the beginning, which sums all types of energy, potential, kinetic, etc., has to equal the energy at the end. So it can only change form of energy, like such as potential energy becomes kinetic energy. Say we have this ball up here. Right now, when we're holding it up here, it only has potential energy. But then when we drop it and it comes all the way down here, now it only has kinetic energy. All that potential energy has been converted to kinetic energy. So mgh equals 1/2, can't write with the mouse, 1/2 mv squared. And basically from this you can figure out how fast it's going at the end. And you don't need to use Newton's laws to figure that out. Mass, of course, cancels here. Yeah, that's about it. Anyway, anywho, moving on. I have an example problem. So, a rocket is at rest on the launch pad and has an initial mass of 100 kilograms. After burning its fuel for 10 seconds, it has a mass of 80 kilograms, a forward velocity of 75 meters per second, and an altitude of 300 meters. And it asks, what was the potential energy of the rocket motor? Now, this potential energy, it doesn't come from gravitational potential or anything like that. It's basically the energy stored in matter. When the chemicals in the engine change form, energy is released. So there is also chemical potential energy, and I don't really, that has something to do with chemistry, but we're just going to come up with a number. Energy, by the way, is measured in joules, which equals 1 joule equals kilogram meter squared per second, or is it per second squared? Oh, it's per second squared because we would have mv squared. So, all right. So that's what 1 joule equals. Anyway, so how are we going to go about computing this potential energy? Well, we'll use this principle. E at the beginning equals E at the end. So we just have to figure out all the types of energy that it has. At the beginning, all it has is the potential energy because it's at rest at ground zero. So it has no kinetic, no gravitational potential. It just has this potential energy of the rocket motor. Now, at after it has burned its fuel, what kinds of energy does it have? It has forward velocity, it has height, so basically has kinetic and potential energy, gravitational potential. Let's calculate this out. So, the potential energy we're looking for, the potential energy of the motor, equals mgh plus 1/2 mv squared. So this m is the same, and it's the m at h, and this is the m at this velocity, which is 80 kilograms. You will notice that I gave you some extraneous information. We don't need the initial mass. We don't need how long it took to get to that point. We just need this value, and this value. So plugging that in, 80 kilograms times 9.8 times, what was the height, 300 meters, plus 1/2 80 kilograms times the velocity, which was 75 squared. And I didn't actually calculate this yet, so let me plug it into my calculator real quick. 80 times 9.8 times 300 plus 0.5 times 80 times 75 squared is equal to, it's a rather large number. I'm going to put this in kilojoules. It's 460,000 joules, which turns out to be 460 kilojoules. So that's the potential energy inside our motor. Okay. Also, let me know in the comments if you can't see this ink very well. I know I'm slightly red-green colorblind, so if you have a hard time, just let me know. Here's example 2. This deals more with Newton's second law. So we have a rocket weighing 100 newtons, and it's producing 500 newtons of thrust. Whoops. Undo. Stop. Okay. So at initial time, it has that velocity, which that's a vector. It's going to be, say we have this xy coordinate system. Say the vertical direction is y. So we would have 10 over and 120 up. That's our velocity. Alright, so it experiences 250 newtons of aerodynamic drag along its flight path, which means it has the same direction as the velocity, except opposite, because drag is opposing the flight. What is the velocity at 5 seconds later? Alright, so let me remember these numbers. 100 newtons, 500 newtons of thrust. What we do now is draw a free body diagram. A free body diagram shows graphically all the forces acting on the rocket. Thrust equals 500 newton. I don't know if I mentioned this, maybe you caught on by now, but Newton is the unit of force. Thrust weight drag equals 250. That's the magnitude. The direction is along V. those are all the forces that we need to calculate the net force. So let's draw a free body diagram. Let's say this is our rocket. Alright, so here's our velocity, our wind velocity v here. And we have weight, which is straight down. We have our thrust, which is along the direction of flight. We have our drag, which is along the direction of flight, but in the opposite direction. So let's sum these up. Let's sum the forces in the x, sum the forces in the y, and then calculate the resultant force. Alright, so sum the forces in the x, we would do alright, so weight doesn't contribute anything. The thrust does. So we would have, let's calculate this angle to make things easy. Theta equals the inverse tangent of y, which I think was 120, divided by x, which was 10. Let's inverse tangent. Let me calculate this quick. I really should have calculated these numbers first. So it equals 85 degrees. 85.2. What? Alright, so we would have t cosine theta, and then minus the drag, which is also, this is also theta right here. So minus d cosine theta. Alright, I'll just calculate this quick. 500 cosine 85.2 minus 250 cosine 85.2, and I get 20.9 newtons in the x direction. And that's in the positive x direction. Alright, now let's sum forces in the y. Can I erase some of this stuff? I don't know how. I'm new to this. I'll just write small. Sum forces in the y. Obviously, we're going to get contributions from all three vectors. So basically just change the cosine to a sine. Weight is only in the y direction. So we would have positive t sine theta minus d sine theta and minus weight. So let's do 500 sine 85.2 minus d, which is 250 sine 85.2, and minus 100 newton. And we get 149, 40, I wrote 50, 49.1 or so newtons in the positive y direction. So once we have our two x components, I mean our two components are x component and y component, we have our net force. We're basically just curious about the magnitude of v here, so our formula, if you remember, was change in v equals f times change in T over M. Mass, of course, equals weight divided by gravity, which is approximately 10. Let's do 100 divided by 9.8, 10.2 kilograms. Alright, so we have mass, we have change in time, and it said 5 seconds later. We have our net force, and if you don't know how to calculate the magnitude, it's a square root of this squared plus this squared, just like the hypotenuse of a right triangle. And we have everything we need. So this equals square root of 20.9 squared plus 149.1 squared. This is times 5 seconds. This is getting messy. And divided by 10.2 kilograms. And our final answer, oh, this is change in velocity, so you got to add it to our initial velocity. Square root of 20.9 squared plus 149.1 squared times 5 seconds divided by 10.2. We get 73.8 is our change in velocity. So if you add that to our initial velocity, which was approximately 120, 10 squared plus 120 squared, square root, yeah, it's 120.4. So V equals V initial plus delta V, and that equals 120.4 plus 73.8, and we have 194.2 meters per second. Now, in my freshman aerospace engineering class, we wrote a computer program that calculated the velocity and altitude and a bunch of other stuff at every point along a rocket's trajectory. So it used this equation basically and just ran through a loop. So yeah, computer programming is kind of useful in aerospace engineering, but I don't think I'm going to end up getting to any of that stuff in this program. Maybe that'll be a separate, maybe that'll be Rocket Science 102. Maybe we'll do a computer program. But anyway, so you know the concept anyway now for some physics of a rocket's flight. Rather thrilling, right? All this messy math. I could have done a neater job, but well, stay tuned for next episode, which will be some basic chemistry and thermodynamics, and that'll be all. See you later.